Hello folks, in this video I want to talk about how we can finally create the equation of a quadratic function from its graph so long as we have the important information. The question I want us to think about first is, what do we need in order to determine the graph? So when I say determine, what I mean is, what information do we need where there is no ambiguity when it comes to what the graph would even look like? So for example, this is a question we asked when we were first talking about linear functions. And could I use just the slope to pinpoint the exact line that someone is asking for? And the answer is, I think clearly no. Because, well, if you only gave me the slope, the line might exist up here, or it might be down here. They both have the same slope, but quite clearly they're different because of different y-intercepts. What about if I only had the y-intercept? Well, that wouldn't work either, or not just a y-intercept if you only had a single point, because sure, that point locks in one point of the graph, but if you didn't tell me what the slope is, well, I could have a negative slope or a zero slope or a positive slope or whatever. In order to lock in a single line, meaning if I give you this information, there's only one line that works, that has that information, you would need either a slope, so a certain rate of change, and a single point on there, or you would just need 2 points because that, in a sense, also provides the slope anyway. So I want to ask the same question, but for a parabola. So what do we need? We need to determine a parabola. And so I'm going to propose for you five scenarios with the information for you to think about. Alrighty, so the 5 scenarios I want us to think about are having the x-intercepts only. Is that enough? Are just the x-intercepts alone enough to lock in the parabola that someone might be asking for? So I'll say maybe this and this. Okay. The other second scenario is, what if you only had the y-intercept? Third, if you only had the vertex. This fourth scenario, is if you had the x-intercepts plus maybe some third random point. Let's call it right there. And the fourth scenario is if you have the vertex and some other point. So I think you should pause the video here. Try these out. See if you can draw exactly one, or could you draw more than one for each scenario. Okay, so I'm going to assume that you pause the video and try to do that. So the scenario number 1 with only the x-intercepts. This is the scenario we previewed in the previous video where, well, okay, I could draw a parabola that goes through them like this. Like so. Okay, that was kind of ugly, but you get the idea, I think. Like so. But I could also draw a really skinny parabola that's really, really steep that maybe it goes like that. And so already the answer there is no. But what if, you're not convinced, like, well, these are actually the same, you just kind of drew it. Funny, you cheated. Well, to that I would say, then what about this one, where it's the exact same shape as that first one, but it's just upside down? And so already we can see that there's going to be more than one. There's going to be at least 2. One that opens upward and one that opens downward. And it turns out, actually, that I was not cheating. You could simply have a bunch of parabolas of different widths that will go through those 2 x-intercepts, no problem. Okay, so the x-intercepts alone, clearly not enough, as we saw in the last video. The y-intercept alone, I think we could kind of expect this one to not work as well, because you could have that one, or you could have, maybe this one. Or again, you could have a graph that opens downward, like so. And so again, the y-intercept on its own is not enough, and neither is the vertex, right? Because we're going to have options to go open downward, or upward. And of course, we could also have varying, widths of parabolas. We could have something like that. Pretend that's symmetric. Sorry about that. Now, what if not only did we have the x-intercepts, but we also had a third point somewhere in there? So given this parabola, we actually know that it can't open upward the way I've drawn it anyway, because it doesn't pass through that third point down there. So that won't work. So I think that this one actually will work, because once you have that third point out there, it kind of in a sense locks in what the curve of the parabola is going to have to end up being. And since it's symmetric, we know parabolas are symmetric, that this point right here has a mirror image point over here, and therefore will kind of set the other half as well. So I know that's not a very, it might not be a very satisfying or rigorous argument as to why this works, but this actually is enough information. If you have 3 points, that 2 x-intercepts plus a third point, and there's actually nothing special about that third point. It could be the vertex or it could be the y-intercept, but it actually doesn't matter. That third point will lock in the curvature of the parabola and as well as its direction. And so that actually is enough. And the vertex with the point is also enough. If I had the vertex here, it has to only curve a certain way. It can't go all the way out here, or it can't be like this. There's only one specific, curvature or curviness to actually hit that second point there. And since it's symmetric, once again, we know that the mirror image is over here, and it has to look like that. Oops, like that. So yeah, if you have the x-intercepts plus a random point, you're good. If you have the vertex plus a random point, you're also good. There's actually a third way, and we might get to this or we might not, but this is for sure something we talk about in Algebra 2. Oops. And that is just if you just have 3 points, and there's nothing special about these actually. They could be literally any 3 random points. This is actually a good activity in Desmo, so I maybe should have shown you there, but I'm not going to here because it did not set it up. If I have just 3 random points right here, nothing special, they're not even symmetric, mirror images of each other, but there is only going to be one parabola that goes through them like so, which is actually really, really neat in my opinion. So these are our 3 methods, or 3 scenarios for which we can lock down a parabola and therefore create the equation for them. And so the one that we are going to focus on is this one.